I know the yes, the first.
Okay, which one? Okay. Does anybody mind if I stand?
Yeah.
And okay, perfect. Yeah, perfect. And there we go. Yeah, perfect. Maybe okay. Everybody can see okay? Good. So I went to the University of Illinois, and since the last 12 years, I've lived in Houston, Texas. And the interesting thing about Houston, Texas is there are three main languages in Houston. The first is English. The second is Spanish, because of Mexico, very nearby. And the third is Vietnamese. It's true. And there are many, many Vietnamese people. And so because of that, we have excellent Vietnamese restaurants. But nothing compared to here in Hanoi. So it's been excellent. Okay, so what I would like to talk a little bit about is some of what I think are the exciting areas that are being researched right now in signal processing. Some of these things I'm doing, some of them I'm not doing. Some of them Professor Do is doing. But I think it will give you an idea of the trends, the directions that DSP seems to be going. And I will also do my best to answer questions and try to guess what the future is going to be like, just like Sydney refused to. Okay. So the thing I'm going to talk about through the talk is that signal processing is fundamentally a quest or search for structure. Some kind of structure in signals that you're trying to either model or extract or process, or compress, or remove, okay? And so what I'm going to do is talk about some of the different kinds of signals that are emerging as important application signals, the kind of structures that are in those signals, and what people are doing to try to process. Does that sound okay? And you can just interrupt me anytime, except for Professor Do. Not allowed. Okay, so this is old school signal processing, right? Analog signal processing, right? This is Sidney Burris style, early Sidney Burris style signal processing, when everything was done in analog and in terms of voltages and currents, and the signal processor was really a circuit designer. There was really no difference between the two, okay? And what we're emerging into, of course, is a world where the first thing that we do with every signal is what? What's the first thing we do? You sample, right? We sample signals because we can put things into the digital domain, discrete time domain, and then we can use a computer, right, to do the DSP, or the processing. So really, DSP people have stopped becoming like analog circuit designers, and they've become more like computer scientists or mathematicians, right? Well, they're all mathematicians, but it's become more discrete time instead of continuous time, right? If you nod your head, I'll just keep going. Good? You agree? No? You disagree? Anybody disagree? So really now, digital signal processing you can think of, if you draw a Venn diagram, it's really at the confluence of three areas. Information, the kind of information that we care about in signals, whether it's your favorite song or not your favorite song, or whether the song is Mindo's voice or my voice, that's information. Communication is very important. Moving information from one place to another is critical. And the third aspect is computation, right? And now we do signal processing on computers, digital computers, and DSP is really at the confluence of these three areas. So I'm going to talk about some different applications today in the information area, communication area, and the computation. Okay, so DSP really is sampling and then some kind of computer program. So I'm going to talk about different kinds of signals, and the important thing, I think, these are what I think are the important themes of signal processing that are emerging. The first is we're moving from simple one-dimensional signals, like time signals, like my voice, like your heartbeat signal, right? Or communication signals we're moving to higher and higher dimensions. More and more important problems with imagery, digital camera type problems, radar type problems, three-dimensional kinds of problems, video processing, right, for not only television but high-definition television. There are all kinds of interesting problems around high-definition television. Volumetric data, so signal processing on cubes of data, volumes, like a volume inside the Earth. Tons of research going on in that, and especially with the price of oil at about $78 a barrel, tremendous interest now in seismic data. Okay, does Vietnam have much oil?
Yes, you have out the ocean.
You're very lucky. Okay, you're very lucky. Okay, what about gas?
I don't know. You have gas? You have gas.
Okay, good. And then, but think, so everyone's comfortable with one-dimensional signals, right? They're signal, I can draw a picture too, but they're signals that vary with a time variable, right? An image has a space variable, an X and a Y. Volumetric data has three dimensions, X, Y, and Z. But now think in terms of four-dimensional or five-dimensional data. So I'll talk about data, and I know Professor Doe is working on problems that involve up to seven-dimensional data. Okay? Very, very important problems relating to things like three-dimensional television for the future. Okay? And just think for 1 second about sampling. If I sample a signal 1,000 times a second, is that very fast? Not so fast. Is that fast enough to capture my voice? Is it? Not very well. Maybe very poorly, but not very well. Okay, because I don't have a deep voice. Right? If I was very white, I would have a deep voice. But now think of sampling an image 1,000 times on the side. How many pixels do I have now? 1,000 this way, 1,000 this way gives me how many samples? 1 million samples. Is that okay? Can we do that? Can we build systems that do that? Sure. Who has a camera phone? Anybody have a telephone? A camera on your telephone? Yeah, some of you do. Well, that's at least 1 megapixel, right? Probably 3 megapixels. Okay? But now think of one of these crazy MINDO data sets that's 7-dimensional. Okay? And think of sampling 1,000 on a side. Okay? How many voxels of data do we have now? 10,000 million, 10 to the 21, huge, right? Do you think we could even build a computer that would store all of this information? There's no way, right? So when we push to higher dimensions, we're going to be pushing towards data that is harder and harder and harder to do DSP on. And so that means more and more research is required. But these are very important problems that people are going to care about or do care about already. Okay, so that's the first, high dimensions. The second is geometrical data. I mean by that data that has some geometry to it. And I'll make that more clear in a second. Another very important theme is distributed algorithms. Okay, the things that Sydney talked about today with wavelet transforms, and probably most of the things you talked about in the class up to now, have been what you would call centralized processing. Where you take the signal, you put it in a computer, and you do processing on it. Right? If you have many signals, you bring all of them to the computer, you do processing on them, and then you get the answer. With distributed signal processing, what you try and do is do processing in many different places at once. Okay? And then somehow do processing independently at different places at once, and then try to combine to get the answer. Have people heard of peer-to-peer networks? People heard of these? Okay, so ideas of using peer-to-peer type ideas are going to be very important. I'll talk about sensor networks at the end. And then finally, Sydney talked about wavelets, but there's crazy representations that are very exciting and important, way beyond Fourier and wavelet type representations. Sydney mentioned curvelets, there's contourlets, surflets, surfacelets, all kinds of very important new transforms that will be being used more and more in the future. Okay, so this is my kind of outline of some of the ideas I'll talk about. So by geometrical data, what I mean is there's some sense of smoothness in some dimension. So what I mean is you normally wouldn't think about doing signal processing on the surface of an object, but it can be very, very important to think in terms of doing the kind of things like Sydney talked about, wavelet transforms, and actually build up multi-resolution views of three-dimensional objects. That has clear geometric structure because the exteriors of objects have very strong geometrical structure. I think that's kind of clear, right? Just look at anything around you. It's got a solid exterior, and there's some smoothness, right? There's some smoothness along the surface. Okay? That's the same thing when you think in terms of images that have edges. So look at the edges here formed by the cameraman standing in front of the background. There's a certain smoothness to this edge, which is exploited all the time in signal processing. This is a seismic trace. Here's where the oil is. Okay, so when you go to work for an oil company, that's what you get really good at looking for. No oil here. Okay, maybe gas, lots of oil here. Clearly, there's a strong geometrical structure here to this data of some kind of smoothness or continuation of these horizons of the Earth stacked up one upon another. Okay, lots of other kinds of data. If you think in terms of an airplane maneuvering through space, it has a smoothness along the track of the airplane. Or if you think in terms of a fish tank with water below and air above, there's some smoothness to this data. So increasingly, we're going to do things like signal processing with these kind of data sets that are much even broader than the kind of things that you've been learning about in this course. Okay, does this make some sense? Hopefully. Okay, so what's all this adding up to? This is really what I talked about earlier. But there's really two themes or two pressures in signal processing. The first is we're pushing the limit on resolution. We want better and better sound quality, better and better image quality. We want better and better video quality. So we're pushing higher resolution, which means more bits, right? More numbers to describe our data. But we're also trying to process more things at the same time. We're trying to process databases of images, right? We're doing face recognition. We're trying to do three-dimensional television. So we're basically, think of multiplying this number, the number of bits per image, maybe millions of bits, by millions of images in a database of images. You think of a picture of every person in Vietnam, right? From multiple angles, so that when they walk to the bank and they try and get money, they just get the money because the bank recognizes them, right? Okay, these kind of things are coming, but that's millions times millions, which is billions and billions of bits that are going to be needed to describe these kind of systems. And the word is deluge. You know what the word means? It means like rainstorm, big time rainstorm of data. Way too much data, more than we could ever do anything with. And so we need to figure out ways to use signal processing to extract the information from this data without trying to store all of this kind of stuff. Make sense? Okay. Keep going when it makes sense. Okay. So one of the keys to making this happen, and this is a colleague of Dr. Doe, is multi-scale analysis. So you saw Sydney's talk. But the critical thing is the idea of analyzing data at multiple different scales. Okay, just think for a second. If you really need to understand the very fine structure of the beard on this person, then you need a very high resolution image. But if all you really need to do is figure out if it was a man or a woman, this picture might be perfectly adequate, right? And this is much smaller than this picture. So the idea of multi-scale analysis is to adapt the scale that you need to solve the problem, the scale of the data representation, to the problem that you're trying to solve. Okay? And the nice thing about wavelets, which this is Sydney's 1 hour talk in 1 minute, is basically we just take an image and we zoom away from the image. We just step back from the image. That makes it smaller, that gives it less resolution. And what do? We take the information we lose. Clearly there's more information here than here. Does everybody see that? Right? There's more information in this picture than this picture because there are more details. We lose details going from here to here. So the thing that we do, these wavelength coefficients, are the detail information that we store, or that we lose rather, going from here to here. Okay? And so the nice thing about wavelengths is that given this picture, very low resolution, and this information, we can build up this picture. Given this picture and this information, we can build up this picture. So the critical thing in wavelengths is you don't never need to store all of these images or data sets at different scales. You just need one data set and then this difference information at each scale. Okay? It's very powerful because this information might be very sparse, not very much information. Okay, so I'm going to talk about some applications, and let's start with imaging. How many people know about imaging? You? Okay, so imaging. Imaging is seeing inside someone's head. Okay, for example. And I should have a picture of Dr. Doe here, but I don't. We might try and find out why this student is so smart. So we like to look inside their brain. Right? So there's two ways that you can do this. The first is the old school way. And they used to do this in France. And you take a big knife and you cut their head open and you look inside. The problem is it's very hard to put the person back together again. Right? Very hard. And so, rather than become surgeons, we want to become DSP engineers. We want to figure out a way to look inside people's heads, for example, without cutting them open. And the beautiful thing is what's called the miracle of tomography. How many people have heard of tomography? Show of hands. Okay, so write that word down, because this is a very useful idea. Tomography. So what's the idea? Very, very simple, actually. You talked about Fourier transforms, right? Okay. So here's the beautiful thing. Actually, let's get a volunteer from the audience. Much more fun this way. Okay. No, you stand there. That's perfect. And actually, you can hand me that one. So here's the basic idea. Or actually, I'll just use it. You stand here. So here's the basic point of how tomography works. I would like to see inside Dr. Doe's head. Okay? Without cutting his head. Okay? So what I do is I shoot things through his head. That's all I can do, right? I can't look inside his head by cutting it. The only thing I can do is have some kind of gun, and maybe the gun shoots away. Maybe it shoots X-rays, or maybe it shoots gamma rays, or maybe it shoots magnetic radiation of some kind, or electromagnetic radiation. And what I can do is I can point this at a certain angle, right? And now I can shoot through his head. Actually, move over here a bit. Right? Yeah, perfect. I can shoot through his head, and then I can put a detector here. Does everybody see this? And now what I'll get is a profile through his head in this angle, right? And he has glasses which really absorb X-rays. So maybe I see very high absorption over here, but then in the middle he's very smart, so lots of absorption. But then in this part of his brain, he's very kind, so it's very soft in this part of his brain, and so it's very, very little absorption. Okay, so I get a profile. And then what can I do now? I can rotate and take profiles from many different angles. Okay, does that make sense? And the beautiful thing, the miracle of tomography, that you're learning about when you learn Fourier analysis, is that if you take these projections through the head, and if you take their Fourier transform, well, actually let me go back. If you take these projections through the head, and if you stack them up in a two-dimensional representation,
you need a pointer or chalk?
Here it is. So I took those projections through Dr. Doe's head. And now if I just stack them up, according to the angle that I took the projections, right? So maybe I have really dense, not dense, really dense, not dense, really. People get me like this? Okay? So I just stack the projections. The amazing thing is that if I take the 2D Fourier transform, what is the 2D Fourier transform? It's the Fourier transform in this way and then this way. That's all it is. I will actually get a picture of what's inside his head. Totally amazing, right? It's a miracle, and it's the miracle of tomography. Okay? And so this is what allows you to make these unbelievably detailed images of the inside of people's heads. Is this basic idea of Fourier transforms that you've been learning about in this class. And it's very, very, very powerful, and it's going to become only more important through time. Okay? The neat thing, though, is that this same idea of shooting things through his head also applies to shooting things not through, rather than projecting through his head, you can also reflect waves from things. And so this is exactly the same way that sonar works. Okay, in a boat, when you send a sound wave right down into the water, it bounces off things and comes back and is acquired by some array of microphones in the water. It's the same way that radar is able to make a picture of the Earth or a picture of Venus through the clouds. Okay? And it's the exact same way that we make these pictures of the underground to look for oil. It's all the miracle of tomography. And that's the beauty of DSP, is one idea, projections give you Fourier transform slices, underlies all of these techniques. Right? So study Fourier transforms really hard, become an expert, because then you can do all of these things. Okay? So that's imaging. Very, very important. Very, very, very important. Okay. Another neat aspect of imaging is moving away from making two-dimensional images to three-dimensional and four-dimensional images. So just to give you an idea, let's say that we want to understand which parts of your brain control different things in your body. Okay? Then you can do an experiment called functional MRI. We've heard of functional MRI. Okay, this is very important. Okay, cutting edge kind of idea. Here's an experiment, and this is not made up. Imagine we did the same experiment with Dr. Doe. Here's his brain. Very smart. Look at that. Wow. Dense. Very dense tissue. Good. Say we did this same experiment with Dr. Doe, but as we took the picture, we asked him to wiggle his finger. Or wiggle your finger while we're doing this. So he's wiggling his finger. And then imagine we don't do this once, but imagine we do it once every second. Or many times every second. Okay? And now imagine if we look at one particular spot in his brain, right? And this is what that value looks like, but now over time. Does everybody get it? Okay? And what we can do is we can actually do convolution. Who knows convolution? Okay? Convolution with his wiggling. Which, and the neat thing is, this is without him wiggling, this is with wiggling, and you can clearly see that if we do a convolution here, we're basically matching up, right, the wiggling of his finger with the actual changes going on inside his brain. Okay? And what you can actually show is that you can detect activity of different sorts inside people's brains. You can tell them a joke, make them laugh, and figure out which parts of their brain are making them laugh. Okay? You can make them do mathematics. 16 times 3.
28.
Okay. You can see what part of the brain does mathematics. Okay? Unbelievably important, not only to understand how the brain works, but also for things like surgery. If you need to remove, say someone has a brain tumor, some cancer, and you need to remove part of their brain, you can do experiments like this, even during the operation, to understand what is happening as you're doing the operation. Okay? So very exciting, very important. And this particular problem you can see is three-dimensional, because we have two dimensions here of space and one of time. But now if you imagine, this is real, this is in Noah's brain. When we told him to add 16 and 12, and you see the price of lights out there. Okay? But doing it in 3D, now this is four-dimensional data. Because what we're doing is we're taking scans in 3 dimensions of the whole head, but what we're doing is we're also looking through time. So we get 3 space dimensions, 1 time dimension, and we're actually finding how parts of the brain react. Okay? Do you believe me that this is really true? Seems crazy, doesn't it? But it's totally true. Okay, so that's tomography. The interesting thing is the same idea of this idea here of correlating, okay, or convolving with signals that you're looking for, okay. Did you talk about match filtering? You're going to. But this whole idea of convolving with signals that you're interested in order to look for them, because the smooth curve is the information, this curve is the data, right? You're trying to pull the information out of the data. The same idea applies on the internet as well. So now if you think in terms of the internet, does anybody know what the internet is? Okay, you know what the internet is. So you have a computer in Hanoi, and then you have a computer in Illinois. What about Ryan? Are there a lot of Vietnamese in Illinois?
Yep.
Okay.
More than 1,000.
Okay. Or Ryan, yeah, because it rhymes, so that's probably why they went there, right? Okay. So, New York City, Ho Chi Minh City. Wow, it's amazing, actually. Okay. He's the only one who gets my jokes. Okay, so the idea, this same idea of projecting through. Remember that we projected through Dr. Doe's head to find out what's going on inside. The same idea of tomography can apply on the internet. So you could start sending some packets from Hanoi, and you could send those packets through to Illinois. But then you could also send packets from Ho Chi Minh City, up here, to Houston. Okay? And you could also send packets from Moscow to Buenos Aires. You see what we're doing? We're going through the internet through different paths. Right? Well, the amazing thing is, the same kind of miracle happens here. That you can actually make maps of what's going on inside the internet. Where there's lots of traffic, where there's not a lot of traffic. It's slightly different mathematics because it's more nonlinear than linear, but the exact same ideas apply. And this is fundamental to many problems in computer security, things like mission control, figuring out if you're going to stream voice over IP, where is the best place to stream it. These tomography ideas are used in a lot of different areas. Okay, so that's for the power of tomography. So now let's talk about an example that's again related to tomography. Sort of like my whole talk is about tomography. But this is about camera arrays. So everyone knows what a camera is. But now the question is, what can we do with a whole bunch of cameras? And we can do very interesting things. So what we can do is we can take pictures of objects from multiple different directions. Okay? And we can use this to do a bunch of things. One, to recognize people. Okay? Another possibility is for things like three-dimensional television. Imagine television, how does television work now? Right? Or movies. They're two-dimensional. There's a camera at a certain point, and there's actors, right, or a scene, and then they broadcast that exact view, right, to your television. So really, when you watch TV, or through here, for example, hello there, it's no different than if your eye, right, looking at your television, is the same as the cameraman's eye right now. Everybody gets the idea. Basically, it's though you were right there. But what if you want to look from a different angle? What if you're in a movie and you don't want to look at the actors this way, you want to look at the actors this way? Okay? Well, very soon, there are going to be systems where you'll be able to zoom and pan around the entire movie scene because they're going to have multiple cameras set up around the scene in order to be able to do this kind of thing. Okay? And this is already used in movies for special effects. Does anybody know what movie was the famous first movie they did this? The Matrix. How many people saw the movie The Matrix? Okay? So when they jump up in the air and it's like they're frozen in time and the camera spins around, that's actually done with a gantry of 32 or 60 cameras where they actually are filming simultaneously. Okay? If you've ever thought about how much data comes from one of these video cameras, and now think about processing 100-fold the amount of data, huge amounts of data. Okay, so camera arrays. So here's an example of a camera array. Each of these is a camera, the size of that camera. This is the Stanford camera array. And what it acquires is actually in this case, a four-dimensional hypercube. That's a cube in more than 3 dimensions of data. Why is it a four-dimensional hypercube? Well, because each camera, how many dimensions does each image have? 2. And then there's how many cameras? They're laid out in a 2D array. So we have a 2D array of 2D cameras with four-dimensional data. So now just think for a second. 1,000 pixels by 1,000 pixels in each camera. 1,000 cameras by 1,000 cameras, that's how many pixels? 10 to the 12. A lot of pixels, right? Forget ever trying to load that onto your desktop computer and do anything with it. Okay? So it's very hard. And Dr. Go's working on, you're doing plenoptic stuff. So it's very exciting, but very large amounts of data. So here's our cheapo array. You could build one of these here. Very, very simple. It's just a selection of cameras that are connected by FireWire to a single computer. And then we simulate multiple cameras in the second dimension. Right? You see this is one dimension. By basically having a turntable and spinning the object on a turntable. Just like the Matrix. Okay? And at Rice, and other people like Mingo and a lot of other people are working on algorithms for doing rendering of these virtual views, being able to use this for identifying objects, okay, from this three-dimensional views and other problems. And I think I will show you a example. Let's go to the example. So here's just a student project. This is something you could do. You build one of these arrays. Big camera array. And it's just about, you'll see what it is, an object. And we're spinning the object. And we acquire the data of the object from all possible angles. And then what we can do is with a joystick, choose a view that we want to fly by the object. So we acquire a whole bunch of pictures, but then we say, oh, I want to go by like this. And we can simulate this kind of view. So here's just the example. So none of these, this is not the way that we acquire the data. This is actually defined by the user, and then this is a virtual flyby of this particular sprite can. Right? You see it's very low quality, but it definitely shows you the idea. And things have improved hundredfold over the last few years on how well you can do this kind of thing. Okay? And the first place you're going to start to see this kind of stuff is in like the Xbox, PlayStation, all of these kind of things. In fact, the world's most sophisticated signal processing computers are game computers. Okay? And there are actually people out there who design supercomputers by installing Linux on a PlayStation or an Xbox and then having an array of thousands of them. Okay? Very, very, you should do this here. I mean, yeah, that'd be very, very cool. This is very inexpensive. You get old ones that people don't want anymore, and you build a big array of them. Very exciting. Okay. This is the last name, the one I'm going to talk about, which is very similar, but this is the idea of what will happen in the world when we will have sensors everywhere. Okay? Sensors everywhere. Imagine having an environmental problem where you have an oil well off the coast of Vietnam near Ha Long Bay, and you want to protect Ha Long Bay, but there's an oil spill from an oil tanker. Well, imagine a world where it varies already, actually. A helicopter, you can fly a helicopter over and drop out hundreds of little nodes, and these nodes can sense whether they sense oil or not. They can communicate amongst each other, and they can send information through a satellite back to Hanoi, where you can make decisions about which way the oil is moving. Okay? This kind of technology is here today, so it's pretty exciting. So the idea now is everybody knows what a microscope is. What's a microscope? See very small things in a very localized way, right? Into one cell of my body. Right? So what a sensor net is the exact opposite. It's a macroscope. So instead of seeing tiny things at a little tiny scale, the idea of a macroscope is to see huge distributed phenomena. like oil and pollution levels everywhere along the coast of Vietnam, or coast of the United States. Okay? So it's basically signal processing, but now on a huge scale. Okay? And there are clearly many reasons why you might want to do this. To sense environmental conditions, pollution, sound, vibrations. You might have fires, and you want to sense where the fires are moving, etc. Okay? So what we've seen in the last 5 years is an explosion of really cheap, what are called sensor nodes, or motes. Okay, these are much bigger than they really are. They're all about the size of your thumbnail, or bigger, or 4 thumbnails. They're very small. They currently cost about $100 US, but within a few years they'll cost $1 US each. Okay? And they'll be equipped with things like temperature sensors or gas sensors, cameras, okay, little cameras, or pollution sensors. And you'll be able to deploy these everywhere. Just imagine putting 10 inside this room, right? Cameras in this room so that you can monitor what's happening, so that the professor can know how many students actually showed up in class, right? Etc. Right? Okay, so there's, let me just say, security is a big issue here too. How do you make these things not be used for malicious purposes? But I'll talk about that. Okay. So the big interesting issue here is it's a, we talk about DSP, and we talk about DSP is sampling and then computing. The big thing with sensor nets though is we deploy a network over some region like a city, and somehow we have to harvest the data out of this network. We need to get the information out. And that's going to require some kind of communication, right? Because these are not going to be connected by wires. They're going to be battery powered, and they're going to be interconnected by wireless, like your cell phone or like your Wi-Fi system. Okay? So these sensor nodes have sensing on them, they have computation on them, they have signal processing on them, and they have communication and networking abilities. Okay? But the critical thing is, if you just think for a second, it takes many, many, many fewer joules or battery power to compute on a bit locally inside one of these systems than to communicate a bit. Okay? Communication is extremely expensive for battery power. Computation is actually very cheap. So what this pushes the world of sensor networks toward is the idea of what's called distributed signal processing, where we don't try to just harvest all the data to one place, but try to actually take everything you're learning about in this class and figure out how to do it in a distributed way. Very challenging, but very important. Okay? So one example of this, I'll just illustrate an example, is distributed compression. Okay? So, I already said, let's say that we have a bunch of microphones. Each of you has 2 microphones, your ears, right? Well, let's say that I'd like to transmit out of this sensor net. Each of you is a node in the sensor net. The sound that's heard at the various different places inside the room. Okay, so how many of you are here? 50? 50? 2 ears per person, 51, 102. Okay, so there's 102 sensors. Okay, so what I want to do is get 102 signals out of my network. Okay, let's say that each signal is 100,000 points long, and I have 8 bits per point. How many bits total do I need to send out of the network? You're the computing guy. How many? 8 bits per point, 102 signals, 10,000, million points long each. So 800 million. Okay, so we need to get 800 bits out of this network in order to get about a few minutes of sound. Okay, and that means 8 million bits, and we each might have a little tiny battery in our sensor node. How long do you think our sensor network is going to last? Yes.
2 seconds?
Yeah, maybe a couple minutes, and that's the maximum. Okay, so that's not good, because we'll do a lot of battery changing, right? We'll have to have a lot of people running around changing batteries, which is not good. we might like our internet to last for a year on a battery. So clearly, this is not going to work. Everybody sees the point, right? Just transmitting raw data out of the network is a bad idea. So the big theme is to realize that my voice is almost the same in each one of your ears, right? It's almost the same. Slightly different, right? But almost the same. So that means that there's all kinds of correlations or all kinds of dependencies between the signals in each of your ears. Should we be able to exploit this in some way? Does everybody see what I'm saying? So for example, each of you had 2 ears. How different do you think the sounds are between the 2 ears? I think we could get a factor of 2 savings by transmitting the left ear signal and then the difference between the left ear signal and the right ear signal. Does that make sense? But how about you and your neighbor? How about we send one of your, everybody look to your left. Everybody look to your left. Nobody looks. Cindy's doing it. Everybody look to your left. Nobody's looking to their left. Okay. Maybe. You're going with that. So imagine if you don't send any information out of the network, but you let the person to your left send the information out, and you just send the difference between you and the person on your left. Basically, then what we're going to have is only the people at the end of these benches sending out data, and then only sending differences all the way along. That's a big savings. Okay? So this is the idea of what's called collaborative sensing. The idea that the sensors shouldn't just send out raw data, but they should collaborate amongst each other, okay? And then only send out this essential difference information, okay? And this is really doing what you could call distributed DSP, or DDSP, right? Everybody say that. DDSP. Okay, so this is DDSP, and let me just give some examples of this. So one example is everything that Cindy talked about, wavelets, you can distribute throughout a network. It's a hard problem, but you can do this. I'm going to skip over these slides. But this whole idea of wavelets and multi-scale analysis, you can actually do in a distributed way. And here's an example of not this audio problem I was giving, but a smooth data field problem. And then these purple dots are the actual sensor measurements. Okay? And there's about 256 of these sensor measurements. But basically what we did is we actually did a distributed wavelet transform across the network. And the curve here is actually the interpolated data that we get looking at these sensor measurements and interpolating or extrapolating the information. Okay? And the first thing you see is you get very nice agreement between the data points and the interpolated or extrapolated data. And the really nice thing is instead of having to transmit 256 numbers out of this network, we only had to send about 32 numbers out of the network. Okay, so we had what is that, 4-fold savings in the amount of data simply by doing one of these distributed type wavelet transforms. And I can talk more about that later. Okay? Here's just an example of this with real data. So here's Intel Berkeley Labs in California. Someday some of you might work there. Okay? And this is environmental sensing inside a building. The black dots are the nodes. And I'll just give you a quick feeling of this. This is light level, and everybody can see that this is how many days worth of data do I have? How many days worth of data?
4 days.
Any guesses?
4 days.
Oh, perfect. 4 days. Why? It's obvious, right? Bright, really dark. Bright, really dark. Day, night, day, night. Right? So there's about 4 days worth of data. 3 nights. And the thing is, why do we need to send data from the network when it's dark? Why can't we compress? And so we can actually use distributed wavelet-like compression ideas. And just look at this curve. This is an example of sending about 10 times less data out of the network, but being able to do in each of these cases a pretty good job approximating these signals. Okay, so you see there's like about 50 signals here, one laid on top of the other, and we're doing a pretty good job of approximating. with 100 times less data. This is humidity levels, so it gets humid at night when the air conditioner turns off, less humid during the day when the air conditioner turns on. Okay, and this is temperature, right? It gets hotter in the day, colder at night. This is in Berkeley, so they can actually, it does get cold at night. Okay, so this is just some examples. This is just on one signal. So this is a very important area of signal processing is moving toward not centralized signal processing, but distributed signal processing. And for people, like I said, who know about peer-to-peer databases, this is very related to those kind of problems, distributed systems. We have a test bed in Peru where we actually test out some of these ideas. We climb up in trees, try not to fall out. Some of my graduate students do this. This is an aerial view from a tree. And we actually put these sensor nodes in extremely expensive housing. This costs about 10 cents. It's just a pipe, plastic pipe with a plastic pipe end, but it works great. And we deploy networks, and we get data from the networks, and we try and do compression, and we learn more about interesting problems. Like one of the biggest problems with sensor nets is not battery life, but having a monkey climb inside your sensor node and steal the little batteries because they're tasty. Okay, or a big spider making a web that heats up the sensor node and burns up. Okay, so it's very interesting problems that are not related to DSPs. Okay, we also have a big project at Rice on building these sensor modes. These are the kind of things that you can actually build. Student projects. I think Rice, the year that they built this sensor mode, this is an American quarter, so it's about the size of a 500 golf piece, I guess, roughly. And they actually built this. This is an all-student project, and Texas Instruments has a program where they give prizes for best student projects. So this is actually a project where they have not only the sensor board, but then a whole bunch of sensors and other things that can plug in. Bluetooth, other kinds of radios. Okay, so I'll wrap up. So unlike Sydney, who refused to predict the future, I will predict that the future will bring higher and higher dimensional data. Okay? We've talked about some of these kind of problems today. And it will bring distributed algorithms. Absolutely. Okay? So these are problems that are going to become very, very important. And we're going to need to come up with new representations, even beyond the things that you're learning about today, to exploit the fact that the structure or information in these signals is somehow going to be geometrical now, and not just the old kind of structure. Okay, so I'll end there. I don't know how much time I do have for questions. Maybe I'm running out of time, Sydney? Yeah, okay, so I'm going to have to go. But I'll be around after over in the next building. If you'd like to learn more about what we're doing, you can just see our web address. And feel free to send me emails with questions, etc. And thank you very much.